Sure,
Okay.
yeah.
So we're happy to have Minhyong Kim, who is the Christopher Zeman Professor of Algebra, Geometry, and Public Understanding of Mathematics at the University of Warwick, and a distinguished professor at the Korea Institute for Advanced Study. And he will tell us this evening / this morning about recent progress on the effective Mordell problem.
Thank you so much for this invitation. Again, I realize that it's evening there, so if any of you feel like just a very general introduction of a colloquium style, even though it might be somewhat insulting to people who are already conversant in the subject to varying degrees, on the arithmetic of elliptic curves, of the algebraic curves, sorry. So the basic problem, of course, is that we are studying a smooth algebraic curve defined over Q. You can do this over other fields as well, but I'll just stick to Q for concreteness now, of genus G. So as you know, genus G means most of the time we're just looking at a two-variable polynomial equation with rational coefficients of degree D, right? Where the genus and degree are related by this formula most of the time, as long as you avoid the singular cases. Diophantine geometry, it refers to when you're looking at this problem from the point of view of number theory, that is, you're interested in rational solutions. So these days, when students ask me what arithmetic geometry is about, I tell them that we're studying mathematical structures that simultaneously have a geometric and an arithmetic structure that interact in some way. And this kind of Diophantine problems is very much typical of arithmetic geometry in that sense. And again, many of you will know that the structure of this problem is actually very much affected by the geometry. That is to say, there are these three rough divisions which carry over into higher dimensions. That's why it's somewhat useful to spell it out in this form. That there's a genus 0 case that corresponds to positive curvature, genus 1 case, the zero curvature, genus at least 2 corresponds to negative curvature, hyperbolic geometry. So it's hard to say exactly how these geometric properties translate into the arithmetic. But over the years, as people have worked on these problems, it's become clear that there are intricate relationships that are not so easy to spell out. And so maybe the difficulty of exactly saying what this relationship itself is part of the charm of the subject, even though they exist. So let me say briefly in turns what's known about this. Even though it seems to be a very simple class of problems, there's still much unknown. In particular, there's something of an embarrassing fact in my view for number theorists, that even after studying these problems, in some sense literally for millennia, right? These are some of the oldest problems in mathematics. The genus 0 case is the only case that's completely understood. This is a fair statement that after all these thousands of years, we only understand one case. So what is this case? Well, the reason we can understand it actually also uses quite sophisticated techniques. You do have to use a part of class field theory and also algebraic geometry. The algebraic geometry part is probably at this point relatively elementary, but still the class field theory part is still not that easy. So how does this work? So I'll just roughly remind you, because it's also a model for what comes afterwards, what happens in the genus 0 case. Very roughly speaking, this is where people consider this thing called the local to global methods, right? In order to solve the first problem of existence of solutions, and then there's this algebraic geometry for generating more solutions. What are the local to global methods? Well, you want to study rational solutions, but you study solutions in various completions of Q, like the reals, 2 adix, 3 adix, 691 adix, and so forth. For each prime, you have a completion, and rational solutions, of course, embed inside solutions inside this field, right? It's this picture that you try to think about Q as somehow being like the intersection of all these completions. It's not literally, because you don't have anything to intersect inside, but it maps canonically to all these completions. So I'm terrible at drawing these pictures, but I drew this once for an undergraduate level talk, and it was so hard that I keep using it again. I feel like I have to make full use of the effort. Right. And in case you're interested, this prime over here is, according to when I last looked at Wikipedia, the largest known prime over here on the lower right-hand side. So you can complete it for any one of these primes. Okay, so what do these categorical methods say? Well, it allows you to study a solution like this and talk about the existence of solutions in the rational in terms of solutions inside these completed fields. For example, if you look at an equation like this, it will have a rational solution if and only if it has a solutions in the reals, in the 2 adix, and then 37 adix, 59 adix, 67 adix. You just have to check for the existence of solutions inside these 5 fields. So, for example, you can easily see that it has solutions in the reals, right? Simply by looking at the sign of the coefficients. For the other fields, it's probably not so evident, but it's worth pointing out that it's, first of all, there is an automatic criterion for checking for solutions inside these kind of complete fields. This one way of phrasing it in terms of a little bit of local class field theory or a fragment of local class field theory. But it's also worth, what is worth pointing out, sorry, I started out saying that something is worth pointing out. It's that method, the checking for solutions inside these other fields, is actually not so different from checking for real solutions. For real solutions, we just look at the sign of the coefficient, and it's roughly similar checking for solutions in these other fields. You just have to do a little bit more checking because these fields have these ring of integers with a residue field that might be larger. So roughly speaking, the 2 components of the reals are the only thing that plays a role here, but the various number of elements inside reduction mod P is what plays a role in checking inside these other fields. But anyways, so I'm not telling you what it is now, but it's possible to check inside these complete fields whether or not there exists a solution. So using that, just by checking inside these 5 fields, you can check whether or not there's a rational solution. So this kind of theorem is called the Hassa Principle, this kind of statement. Now, also, I'll remind you that if the solution is guaranteed, then you can certainly find it deterministically. Somebody tells you it's definitely there, then you keep searching. For example, by listing possible rational solutions in terms of in order of size of denominators and numerators, and you keep searching and you find it, and you find it. And once you found it, then you can find all the other rational solutions using a parametrization method. So some of you may have seen that when you are looking at this equation, for example, x squared plus y squared equals 1, you can generate all the rest from the easy solution 0, minus 1, and you get a generative solution like this given in the parentheses. And this is called the method of sweeping lines. But this works for any genus 0 equation. Once you have one, you can generate all the others by considering lines of rational slope that pass through this one. And then the other point is guaranteed to be rational. So that's the genus 0 situation. And I'm drawing the picture for the circle, but this works for any of these genus 0 equations, the same idea. So here I'll just make a slightly cryptic remark because I'm not going to really allude to this too much for the rest of the lecture, but it's an important point of view that actually, in some sense, in the genus 0 case, it's possible to study the way the rational solutions sit inside the product of all these completed fields. This is actually a possible thing. And there's a sense in which class field theory does this for you. It allows you to study this inclusion in a successful way. And that's why what underlies our ability to understand completely genus 0 equation. Now, what happens in genus 1? So now already at this point, all hell breaks loose. So everything is harder. So for one thing, well, okay, the solution might be empty, it might be non-empty finite, it might be infinite, all these possibilities exist. But furthermore, the Hassa principle I referred to earlier fails. So if you look at this equation, for example, this is a cubic equation, degree 3 is the genus 1 case. This has a solution in all the complete fields, and you can check that, but it has no rational solution. As far as I know, this was historically, I think, the first curve where people made computations of this sort and started formulating the difficulties surrounding this local to global principle. This is due to Selmer, I think. So it's hard to check whether or not a solution exists. And secondly, even if a solution exists, and even if you have one, it's very difficult to describe the full set. Ideas similar to the genus 0 case exist, but they're hard to implement. So you probably know that once you, what do I mean by idea similar? That once you fix a rational point and decide to regard that as an origin, then that you can put on the side of rational points the structure of an abelian group. And this is called the Chords tangent method, described by this picture, right? If you want to add A and B, you draw the chord, the secant line through the 2 points, and that meets the curve at one other point and reflect it across the x-axis. That's A plus B. And so you can also add A to itself using the tangent line. So that's the chord tangent method. And you get this group structure. So that's very useful, of course, because this gives you a way to sort of organize the points and try to generate new ones from old ones and so on. And the big theorem that started up sort of the more elaborate structure theory of elliptic curves, that's what these are called, is the theorem of Mordell that says the rational points, in fact, form a finitely generated abelian group. So there's this infinite part, the free part, z to some finite number r, and there's this finite part, the torsion subgroup. So of course, if you think about it, it is a remarkable theorem, even though it's very easy to prove at this point. Because if you look at the complex solutions of these equations, then they form tori. So there's S1 cross S1. That's a very big group, cardinality-wise, right? But these are countable, finally generated groups, the rational solutions. And Mordell's theorem says that very precisely. Now, the torsion part is very easy to compute. This is what you learn in the first course on elliptic curves. So for example, if you present the elliptic curve as y squared equals xq plus ax plus b together with this origin, which is the point at infinity in projective space, then there's a theorem of Nagel and Lutz that say that a torsion point necessarily has integral coordinates. Even if you a priori allow them to be rational, they are necessarily integral. And y squared has to divide this quantity, called discriminant of this cubic. So this is, of course, very easy to compute if you're handed an equation, right? So it's possible to check for all cases, right? And find the complete set of torsion points. This finite part is easy to find if you're presented with the equation. But the algorithmic computation of the rank, that r in the z to the r, and a full set of generators for this finite free part is very difficult. And this is the essence of the conjecture of Birch-Swinnerton. How do you compute these things? So as you know, this is one of the most famous open problems in number theory, and it's quite hard to resolve. But there's an interesting aspect of this conjecture and the difficulty surrounding it, which is that in practice, there are all kinds of programs that tell you that it's okay. Yeah, so for example, if you take a curve like this and you give it to an algebra program like Sage, then it will immediately tell you that the rank is 1 and the point 3, 5, the obvious rational point, is actually a generator for that free part. This has no torsion subgroup, that's 0, and in fact, there's only there's one generator, and the group of rational points is Z. So this is interesting. Almost any reasonably small coefficients you plug into Sage, it'll compute all these things for you immediately. So it's a bit puzzling when you hear about all these difficulties, how it actually does this. And I'll say a little bit more about this later, in case, unless you're completely bored by that discussion, we can skip it. But the point is that these programs that compute the rank and the generators actually use the conjecture. The algorithm only works if the conjecture is true. So each time it works, it's a confirmation of the conjecture. It's actually evidence for the conjecture. And so far, every single case everybody has tried, the algorithm works. So somehow we have a lot of evidence for the conjecture from that point of view. So I'll say a little bit more about this, elaborate on this a bit more later. Now, also, I'll just point out for people who haven't seen this before, you can compute the multiples of this point according to the group law, and you get these very large denominators and numerators, very quickly as you compute. And so it's kind of fun to display all of them. I don't know if you can see this these are all numbers. Oh, sorry about that. These are all numbers. So what I've done is I've taken something like the first, I forgot, 15 solutions after you, the first 15 multiples of 3, 5, and put the denominators of the x coordinate and organized it like this. It's very pleasant to see. Something like this happens with every curve, by the way. Each time you take a point of infinite order, you see a picture like this. Namely, this outline is always a parabola. So that's a theorem as well that comes from the theory of elliptic curves. So that's a fun thing to try out. If you've never tried out before and you'd like to learn about elliptic curves, go to Sage and compute multiples of some points, and you ask it to compute a point and then compute some multiples, and it's fascinating to see this picture emerge. Okay, so that's genus 1. So, sorry. Let me now talk about the genus 2 case, genus at least 2 case. So this is where I've spent most of my time over the years. So here you have this remarkable theorem of Faltings, which is now already almost 40 years old, that says that the set of rational points is always finite. This was called the Modal Conjecture. And for me, when I was a graduate student, this was sort of the theorem to understand and try to work around. Now you can imagine, maybe you can't, but if you look at this equation, you can imagine that it's actually very hard to compute this finite set. Even if the theorem guarantees that it's finite, right? To actually list that finite set is very difficult because, for example, if you consider this for these Fermat equations, the theorem applies to all of these. But as you know, there were these few obvious solutions, but to know that there were no more took hundreds of years. And that's the typical situation when you write down equations of genus at least 2. You know that there's a finite solution set. Sometimes there are a few obvious ones. These are in some sense the most difficult cases. Sometimes it's possible to prove that there are no solutions using sort of easy congruence methods. But if it happens that there is a solution or a few solutions, it's very, very difficult to check that there are no more. So these Fermat equations are a good illustration of that, where, as I said, it took hundreds of years to prove that there are no more. So that's the difficulty of this kind of problem. Sometimes it's easy, of course, if you look at this, but sometimes it's not. If there's not an obvious reason for non-existence, you write down a random equation like this, right? Now this has the solution 1,729. Obviously is a joke. I generated this non-obviously, but even for this equation, I still don't know. I just wrote this down and I said maybe one can figure out somehow using some of the existing method whether there are more solutions or not. I still don't know whether there are any other solution. Maybe some of you are very clever with this and can spot some of that right away. But even if you did that, to actually check that there are no more than that would be very hard. So that's the typical situation with these equations, the genus at least 2. So that's the effective Mordell problem that appeared in the title of the lecture. Can you find the terminating algorithm that lists the set of rational solutions if somebody hands you a curve? And this is still a very much open problem. Right? So up to the 1990s, there were a series of conjectures, sometimes called the effective Model conjecture, due to a bunch of people. The ABC conjecture actually falls into this range of ideas that says that if you hand somebody a curve, you should be able to write down a bound, an a priori bound on the numerator and denominators of possible solutions. That was the effective Model conjecture. The conjecture being specific bounds, which is also predicted by a refined version of the ABC. So people worked on these kind of problems for a long time. As you know, the ABC is still one of these controversial subjects. Right? And maybe it did something there. But actually, by the way, it was with the proposed proof of the ABC conjecture in the existing form, it still doesn't give you this effective version of the Model conjecture. So it seems to be a very difficult approach to this problem. What I've been doing for quite a few years now is doing approaching this problem from a different point of view, not in terms of a priori bounds, but something much more algorithmic in nature, which uses, instead of these Archimedean height inequality, non-Archimedean geometry, arithmetic geometry of principal bundles. So that's what I'll try to describe for the rest of the lecture, what this is about. But anyways, I hope the nature of the problem is clear enough, and I hope people do see that it's quite a difficult problem in many ways. So actually, are there any questions now? It is a suitable point to pause. No? Okay, otherwise we'll move on. So I was going to, okay, yeah, so actually, let me tell you what the basic idea is, a slight problem, before moving on to the technical discussion. So part of it is actually this local to global principle. We start out by embedding the rational solutions inside the completed solutions. And I guess I didn't say it in this way before, but always the solutions inside these completed fields are much easier to understand than solutions inside Q, and you can actually compute them to a large extent. And roughly speaking, this is because for the same reason that we can draw pictures over the reals, right? These are much more geometric in nature compared to the arithmetic set of rational solutions. So there are many techniques for understanding them. These are genuine geometry, whereas ordinary geometry, whereas rational point is really arithmetic geometry that's hard to understand. So what do? We take this inclusion and replace it by, not exactly replace it, but we fatten it up to a different inclusion. So into a diagram like this, where this M, so first of all, there is a diagram that subsumes the inclusion of rational points. So what are these things? Well, these are, I should have written this first. M is a moduli space of principal bundles. And so are the M sub B. There's one for each local completion, and there's one global one. Right? And the global moduli space maps to the product of the local moduli spaces. So points, this is of course a ubiquitous problem in number theory. A point by itself has not much structure. So you try to use it to parameterize things that have more structure. In this case, it turns out to be principal bundles. And having constructed this moduli space, you put those into the local corresponding local moduli spaces. And then the strategy, this is slightly inaccurate, but it's essentially accurate, is that the rational points on the curve should be realized as an intersection between this moduli space of principal bundles and the local points of the curve. So you can refine the Hassa principle, in other words, by using this moduli space. Try to describe this rational point as an intersection. So these moduli spaces themselves are sort of arithmetic gauge theoretic in nature because they are moduli spaces of principal bundles. So it has a geometric structure that's very similar to what you encounter in geometric gauge theory. And that's what I'm trying to use to understand this problem. So that's the big picture. So maybe one thing I'll also say is that because it's kind of interesting and what the technical discussion afterwards might not be as much interest, maybe I'll make a few historical remarks about this picture because the history is actually quite interesting to me anyways, which is that this study of this idea of using principal bundles for studying rational points is actually a very old one. This was first, as far as I know, André Weil used this in principle in his thesis, in his dissertation in 1929. So what did he do? He took a curve like what we have and embedded it in his Jacobian, which he constructed as an abelian variety of dimension G. So this was the first use, I think, of principal bundles in Diophantine geometry. Now, I said that Weil did this, but versions of this go back to the 19th century. So for example, in the 19th century, Jacobian was already constructed as what we would now describe as a complex torus. They didn't, I think, quite describe it in this way, but this would be the dual of the holomorphic differential forms divided by the lattice of first homology. And the map was simply defined by associating to any point the functional and holomorphic differential forms given by integrating, which is well-defined modulo the lattice. So this embedding is what's known in the 19th century, but what did Weil do? He constructed all of these things as a projective variety and the map as an algebraic map of projective variety in such a way that everything is defined over a field F if the curve and the point are defined over F. So that's what Weil did. Why did he do that? It's because this way, not only do you have a geometric embedding, you have an embedding of points. Oh, sorry, I forgot to say. One reason one way to think about why everything is defined over F is, of course, because this Jacobian is a moduli space of line bundles or principal GM bundles. That's the reason that you have this descent to this well-behaved field of definition. And the application they had in mind was that you could put the rational points of a curve into the rational points of the Jacobian. And he also proved that the rational points of the Jacobian, generalizing Mordell's theorem, was actually a finitely generated abelian group. And so in his thesis, he thought that you could somehow use this fact to prove the finiteness of rational points through the Modal Conjecture. So that was the first serious attempt that I know of proving the Modal Conjecture long before Faltings, but he didn't quite succeed. A few years, about 10 years later, he tried again. So that's this very famous paper called The Generalization of Abelian Functions, which I think touches on the research of at least Emily and Jordi, I think, in some way, which is that that's this construction of what we would now call the points of the moduli stack of principal GLN bundles on the curve. Right? Then they thought of this as a kind of non-abelian Jacobian. I know that not many people know about this paper, not many people have read it, but interestingly, he spells out very clearly in the introduction that he is thinking of this as a non-abelian Jacobian, and he would like to use it for something like the Modal Conjecture. That is his motivation. So, and one way of thinking about this motivation is if you should go back to the Jacobian, this is a finitely generated abelian group, the points of the Jacobian, it's not finite. And of course, the finite generation thing gives it more structure, but it also allows the points to multiply. So somehow that makes it hard to go back to the curve itself. So he thought that somehow if you constructed something like the Jacobian that has a similar nature, but isn't a group, maybe it would be more helpful in proving finiteness of points of the curve. It was a vague expectation, but generally speaking, he wanted a non-abelian Jacobian. And this paper, as some of you know, it was very, very influential, of course. I mean, it led to non-abelian Hodge theory. I mean, there's work of Narasimhan and Seshadri, work of Donaldson, work of Collar-Simpson, and all this use of gauge theory techniques in geometry and topology. And Sayre summarizes this paper in an obituary for Vey as a text presented as analysis whose significance is essentially algebraic, but whose motivation is arithmetic. That's a fair characterization. Well, I read Sayre's obituary. It's not quite right either. There are a few things that he seems to be missing about what was going on in that paper, but this characterization itself is reasonable. But as I said, the interesting point is that this paper was extremely influential in geometry, geometric representation theory, topology, and so on. But somehow, the original motivation of trying to prove the Mordell conjecture using this moduli space never happened. And that's still an open problem. So people who like the geometry of this moduli space, that's an interesting problem to think about. I just intuitively suspect that we now have the technology to prove the Modal Conjecture. Actually, there is interesting enough interaction between its geometry and the points on the curve, and you might be able to do something serious, but it is still an interesting problem. Can you realize Vey's expectation from the 1920s and 30s? But anyway, so that's the history of principal bundles in arithmetic geometry. And it's also interesting, as I said, that the motivation for studying a lot of the moduli spaces actually came from number theory. But that's not what I'm doing here. I'm studying moduli spaces of arithmetic principal bundles in a somewhat different sense. Okay? I think what I'll do is, well, okay. So I'll tell you what I mean by arithmetic principal bundles, first of all, from a very down-to-earth point of view, rather than kind of topos theoretic point of view, although that's somewhere in the background. So the concrete view is something like this. What do I mean by an arithmetic principal bundle? So first of all, of course, the simple cases of a principal bundle is if you just have a group and a set with a transitive group action, R action. So a simple transitive R action, that's a kind of set theoretic principal bundle. So, but let's remind ourselves briefly that if you choose a point in P, therefore you get a bijection just by letting the group act on that point. But all these objects, of course, could have more structure. So for example, they could have a topology. These could be topological groups and topological spaces. Or they could vary over a family. This is the case of a principal fiber bundle, right? You have a space M and a fiber bundle over M that locally looks like the group and on which the group acts so that whenever you choose a section, you get an isomorphism from the product R cross U to the portion of the principal bundle over U. So all of these principal bundles, you can start from a point, you can have more structure, it can vary over a space. So we're used to this in geometry. Where does the arithmetic come in? Well, I'll sort of phrase it in terms of this triple. You have a group, a Galois group, and a normal topological group and a normal topological space, if you'd like. So here I'll just for, it's not so important, but I'll fix K to be a field of characteristic 0 and take, so GK here denotes the absolute Galois group of the field, of the automorphism group of the algebraic closure. And so this is a topological group with various open subgroups indexed by finite field extensions of K. When I talk about a group over the field K, what I'll mean is a topological group R equipped with a continuous action of this Galois group by group automorphisms. So this is what I'm saying, has a topo-theoretic formulation which makes it sort of look more conceptually fancy. But anyways, concretely, you can think about such a thing as being defined over R over K in some sense, if it has an action of the Galois group. It's the abstract framework is family of groups over this space spec of K, but anyways, we don't need that view so much right now. So for example, a very easy example is if you actually have an algebraic group defined over K and takes its K bar points, so GLN or something, right? Then just regard that as a group with a discrete topology and it has an action of the Galois group. But this case isn't the main thing that I'm interested in. This is actually important as well in number theory, but it's not, it doesn't have as much information as some of the groups I'm about to discuss. So a better example is something like this. What you do is you consider the group of p to the p power roots of unity inside K bar and take the limit of those things, inverse limit. So what that means is that you have a sequence of p power roots of unity that are related to each other by p powers. Those are the elements of this group. Right? So this is sometimes denoted as ZP1. This set of sequences, and as a group, it's just isomorphic to the p-adic integers because mu p is isomorphic to z mod p. But in fact, the difference is that because they're inside K bar, they have a continuous action of the Galois group. So this is a typical example of a group over K in the sense that I'm discussing right now. It's a topological group with an action of the Galois group of a natural sort. A principal R bundle over K is the same type of thing. It's a principal bundle, but again, equipped with a compatible action of the Galois group on the left, which I'll write as a left action, and a right action of the top of the group R over K. So it's a principal bundle in the usual sense, a tempo transitive action, except there's also a compatible Galois action. That's what I mean by principal R bundle over K. Now, in this case, so you can set up the categorical formalism carefully. I'll skip most of that, but I will point out that the principal bundle is trivial. Trivial means it's just isomorphic to R itself, right? But in this category, what that means is it's trivial with the Galois action. And it's easy to see that that's true if and only if this principal bundle actually has a point fixed by the Galois action. So you can see there's a non-trivial criterion, depending on what your construction is. If you have such a thing, you get an isomorphism between R and P with the Galois action, again, just by acting on Z. But just picking a random point will not give you such an isomorphism because you're considering with the Galois action. So here's an example. So we had this ZP1 a moment ago, which was our R. How do you get the principal bundle? You fix any point in a non-zero element inside K and consider P power roots of that instead of 1, compatible system with P power roots. So that's a principal bundle for ZP1 because, of course, the P power roots of unity were permuted at every level. And so it's easy to check that this is trivial if and only if X admits a P power root in K for all N. So that's kind of non-trivial criterion for triviality. So for example, if you have a field like C, of course, it's always trivial. But if you have a field like Q, it's very rarely trivial. It will be trivial only if X is 1. Right? or P is odd and X is -1. That's the only case that there are rational P power roots for every N. So this is highly non-trivial. If you take a field like R and P is odd, then it's trivial again for all X, but for P equals 2, it's trivial if and only if X is positive. So the point of this slide is to just give you some sense of how arithmetic properties are built inside the triviality of principal bundles, in the setting that we're discussing now. So I think what I'll do is, I realized that I'm talking more slowly than I expected, so there's not that much time. So what I'll do is, I'll skip a little bit of the discussion of how one sets this up and just point out that you can classify these principles. I'll just put the slide in front of you. You don't have to read it. This is kind of standard if you already know about it. Otherwise, it looks a bit weird. But you can classify isomorphism classes of principal bundles using a non-abelian cohomology set. Cocycles modulo on equivalence relation. Right? And cocycles are functions from your Galois group to the group, right? And you modulate by some equivalence relation, and you get something called non-abelian cohomology, which is a pointed set simply that classifies principal R bundles with compatible G action in the set that we, the sense that we described. So this is a simple version of the kind of moduli space that I referred to earlier, moduli space of principal bundles. So there's the part that I just put on the slide and didn't really describe. That induces a bijection between isomorphism classes of principal R bundles and this non-abelian cohomology space. And so in fact, so I'll just restate again what I already did. Our main concern is the geometry of this kind of non-abelian cohomology spaces. You can do this in many different settings, and all of them, in my view, all of them are kind of interesting. They mostly have some kind of interesting implications to different types of mathematics. And we're going to choose the R carefully, in our case, to have applications to Diophantine geometry of a rather direct sort. Actually, so it is a brief remark. So for example, moduli spaces of Galois representations that number theorists are very interested in, at least since the time of Wiles' proof of Fermat's theorem, is also a moduli space of this sort, for example. And there, the natural geometric structure tends to be things like p-adic analytic spaces. Right? But depending on what R is and what kind of conditions you put on the principal bundle, you get moduli spaces with different kinds of geometry, mostly non-Archimedean. And they all have interesting applications, I think. Now for Diophantine geometry, to connect it up with this big general principle slide that I showed you earlier, the point is that you can consider these things over Q or over completions. Right? That is to say, for any completion, you have an inclusion of this local Galois group into the global Galois group. So what this means is that if you have a principal bundle over Q, you can just restrict the action to a local Galois group action, and you can get a principal bundle over QV for every completion. So there's a localization map from global principal bundles to collections of a local principal bundle. So there's a local to global problem for principal bundles associated with this localization. And to sort of continue my grandiose claim from the earlier slide, in fact, very wide range of problems in number theory rely on the study of the image and the kernel of this localization map of this sort. So in our setting, of course, we're going to try to compare this kind of localization with the localization of points, inclusion of rational points of a curve into products of local points. Okay, so just to give you a brief illustration of this idea, maybe I'll just say something about the case of elliptic curves, because it's this is very, very well known. This is not my work. It goes back to the 1960s and in inception. And then people refined the ideas over the decades. But there as well, already for elliptic curves, you can phrase it in the language of principal bundles, although it might be a little bit of overkill in that case. So I'll do it anyways. So what happens there So the picture here is that you have an elliptic curve over Q as of the sort that we started out with. And then you can take the Q bar points of the elliptic curve, right, and consider the multiplication by P map. So then you get an exact sequence. This thing in the kernel is that's by definition just a P torsion. So it's by definition the kernel of this multiplication by P map. Over Q bar points, the multiplication by P is surjective. So you get a short exact sequence like this. You can always solve over Q bar the P division equation. So then when you act on this by the Galois group, you get this well-known long exact sequence where you replace all the Q bars by Q, and then over here on the right-hand side, it's no longer surjective, so you have an H1. So what we'll do is we'll concentrate only on this portion, on the connecting homomorphism part, that gives you an inclusion of the rational points mod P into this H1. This H1 now is a moduli space of principal bundles for the group EP, for this finite group EP, in the sense I described earlier. So here you've put rational points into principal bundles. You could say, this is not an exaggeration, the central problem in the theory of elliptic curves is really identifying this image. In other words, you want to figure out how to compute this H1 in some way, right? And describe precisely how the rational points sit inside the H1. That is the source of most of the kind of interesting Diophantine work on elliptic curves. So maybe I forgot to write this, spell this out on the slide, so maybe I'll say in words. If you, essentially for elliptic curves, if you can compute this group, there's a fairly straightforward way to compute the whole Mordell group. It's not so hard to go from mod P, Mordell Weil group mod P, that's what it's called, Mordell Weil group mod P to the whole full Mordell Weil group. So this is actually the main thing. How do you understand exactly? Describe precisely. What does describe precisely mean? It means compute the structure, of course, but somewhat more. It means computing rational points that represent all the cosets. If you can do that, right, then that gives you, that allows you to compute the full Mordell Weil group. Meaning it allows you to compute generators for the full Mordell Weil group. Okay, so that I didn't spell out, so I'm just saying it again. So I'll just repeat myself because I think I got my sort of tongue-tied in the process. Computing this group in the sense that computing its structure and finding a set of actual representatives for the cosets inside EQ is the same as computing, well, implies an easy method for computing the full Mordell Weil group. So this is what you actually want to compute in the theory. In order to do this, the first step is to cut down the possible image a little bit. And this is what the notion of a Selmer group. So what is this? This is simply the principal bundles inside this H1 that locally come from points. So here already, this idea of refining the Hassa principle plays a very important role. So I'll just throw a diagram at you to illustrate. So you can, this inclusion of Mordell Weil group mod P into the H1 exists at the local level as well. So the Selmer group, we're talking about those things in here that locally lie inside the image of the points. This is a useful notion. Why? Because as I indicated earlier, the image of the points is actually possible to compute locally. We don't know how to do it globally, but locally you can compute the image of the point. So the Selmer group is simply the intersection of all the points, all the principal bundles that locally come from points of the graph. That's what the Selmer group is. Pth Selmer group. And the key point is that the P Selmer group is actually a finite dimensional FP vector space. That's what you can prove using sort of general Galois cohomology and algebraic number theory. And it can be effectively computed. So this group turns out to be an effectively computable group. And this already gives us kind of an upper bound on the Mordell Weil group of the elliptic curve, but we want to precisely identify the image. And how do you do that? Well, what you do is you do the same thing mod P to the n for every n. That's a general strategy. Well, if something in here lies inside the image of the Mordell Weil group, then of course it will also lie inside the image of the map from P to the n Selmer group to the P Selmer group, because this map on the left is of course surjective. So this map also has to It has to hit those things inside the image of this. So in other words, so to get obstructions for a point in here to come from an actual point of the curve, or a principal bundle to come from actual point of the curve, it has to lift to a principal bundle mod p to the n for every n. So that's the something that follows easily from this diagram. And the BSD conjecture, or at least the Tate-Shafarevich part of the BSD conjecture, is that that's the full obstruction. That if you take the intersection over all n, if you take those classes in here that lift modulo p to the n for every n, that should exactly be the image of the Mordell group. So that's the conjecture. Now, of course, since this is a finite dimensional vector space, if this infinite intersection is true, of course, it has to happen at some finite level, right? So how does this, do the computational algorithms work in practice? Well, it keeps computing these guys, these images of the Selma group mod p to the n, as you take n higher and higher. And simultaneously, it still keeps computing points with larger and larger numerator and denominator, right? Possible points. So it keeps generating points. And then it's on the one hand, this left-hand side, in some candidates for the left-hand side grow bigger and bigger. The right-hand side gets smaller and smaller. What does BSD say? BSD says that at some point, the two things have to meet. And once they meet, you know you're done. You've completely computed the image. And you found a set of representatives for the Mordell group mod P. That's the way the algorithm works. And now, but the point is that this algorithm is what's actually used, that is, by all the computers, but it's not guaranteed to terminate. It only terminates modulo BSD. But it's okay, because we believe, if you just believe the BSD and run it, then when it'll terminate, and once it's terminated, you don't need the conjecture anymore. You've actually computed the Mordell group. So in that sense, I like to view the BSD conjecture as being like a theory of physics, right? You don't prove theories in physics, you just use it to make various predictions, right? And what predictions you can give you various insights and tell you about phenomena anyway. In this case, it allows us to compute, the theory allows us to compute the Mordell group anyway. Now, it doesn't mean that you shouldn't try to prove the conjecture. It's also in mathematics, we also like to prove the conjecture. But to some extent, good conjectures and theories are, as far as understanding the phenomena of mathematics is concerned, they're useful regardless of their provability for the existence of a proof, if they're plausible anyways. And now we have tons of experimental evidence that it all works. Okay, so that's the picture. And roughly speaking...
Just quickly, could I just ask quickly, why does BSD say that this should terminate? Are you able to say that quickly?
Yeah, sure. Yeah, so that's this fact that... so I didn't tell you that if you go back to this exact sequence, it's because I didn't tell you what the co-kernel of this map is. The co-kernel of this inclusion is the P part of the Tate-Shafarevich group. Okay. So, and that's true for every level. And so the theorem, the conjecture is that the Tate-Shafarevich group is actually finite. Right? That means that if you take P to the nth power, eventually the maps from the P to the nth part of the Tate-Shafarevich to the P to the n minus 1th part and P to the P, although if you go all the way down to the Pth part, eventually that map is 0. Mm-hmm. So in fact, this has to be surjective eventually. So that's the finiteness of Shah that I'm invoking here. Okay, does that make sense?
Thank you. Yeah.
Any other questions?
Could we have a short break to refill our tea? Is this a good spot?
Sure, yeah, of course, yeah. But maybe I'll just conclude this portion now by saying that essentially what I've been doing for many, many years now, embarrassingly large number of years, is trying to generalize this picture to curves of higher genus. It's exactly this that I'm trying to figure out how to do for curves of higher genus. Okay, so we'll take a break, I guess. For how long is the break? Okay, so now let me move on to this story of how one tries to generalize, extend this elliptic curve picture to higher curves of higher genus. So it turns out that really the main principal bundles of interest is just this, that the group is a fundamental group of a space with some base point. And then the principal bundle is just a homotopy classes of paths from your base point to some other point. This is all it is. So as you know, yeah, sorry, I think I've sort of used notation inconsistently here. I got confused at some point. But anyways, the loops act on the paths by this precomposition. So this is a well-known thing from elementary topology. And so these two sets, of course, are isomorphic. If you choose a path, then that induces an isomorphism from the fundamental group to the homotopy classes of paths. We like to say that, some of us like to say that this isomorphism is not canonical, but that distinction seems to be quite pedantic when you do ordinary topology. But then, depending on what kind of structure M has, these fundamental groups can pick up other kind of structure where this distinction is very far from pedantic. So that's what I found out is interesting to do in the case of Diophantine problems. So it's kind of, even if I look at it myself, it's kind of very offbeat, kind of a stupid idea, that is to say. How can you possibly use these kind of principal bundles to actually study the arithmetic of points? But it has seen a little bit of success anyway. So this has made me very undisciplined in my life in mathematics, that this kind of stupid idea actually works. So it makes me try to come up with other stupid ideas. But anyways. I have to refine to realize what I said just now. I have to refine the fundamental group just a little bit. So that's this idea of unipotent completion. So here I'll just give you a very rough sketch of what this theory is about. And here I'll talk about QP unipotent completion for the field QP. You can do this for any field of characteristic 0. You can take Q unipotent completion, R unipotent completion, C unipotent completion, anything. And the general idea is that it's roughly like taking the tensor product with QP. You end up with an algebraic group from any group, discrete group, via something like a tensor product construction. And then for these bundles of paths, principal bundles of paths, what you can do is you can push it out. Yeah, I forgot to say, the fundamental group will map to this unipotent completion. So you can use that map to push out the principal pi1 bundle into a principal bundle for this completion, just by taking the product and modding out by the diagonal action. So these are the things that we're actually going to use. So what's the idea of this completion? I'll just give you a very few examples. So as I said, it's well, I didn't say this, I'll say it now. It's the universal QP pro algebraic group, unipotent QP algebraic group, with equipped with a homomorphism from pi1. So that's kind of the abstract definition. Unipotent, by the way, I forgot, I left out the unipotent. Unipotent here just refers to the fact that the lower central series terminates, right? And except it's a pro version of that, which means it's an inverse limit of unipotent algebraic groups. So among such things, there's a universal one that admits a homomorphism from pi1, and that's what this is. Now, there are various concrete ways to construct this, and of course, in order to use this for actual problems, you have to figure out how to describe this in concrete way. I'm not going to do much of it now, right now, but I'll just acknowledge that this kind of definition by itself doesn't tell you anything. But so, for example, just to give you a few examples, if you start with a group like Z, it literally is just taking the tensor product. So you get QP, which is just the QP rational points of the additive group GA, so-called, or A1, right, or whatever they are fine line. If gamma is a two-step nilpotent group, right, the U gamma is kind of a Heisenberg group that fits into an exact sequence like this. So the abelianization will be just there. You literally take the tensor product. Yeah, the commutator subgroup will be an abelian group. Right, so you take the literal tensor product again. So you have a few copies of GA here, another few copies of GA here, and there's a way to canonically construct an extension of this by this, reflecting the original extension structure of the original nilpotent group. So that, so this picture more or less captures the flavor of the unipotent completion. So at all the levels, graded pieces of the lower central series, you're really just taking tensor product. The unipotent completion just patches it together according to the extension data of the original group. And so understanding what this is just understanding the extensions. I guess I won't say much more about that, but other than the fact what I just, to re-emphasize what I said earlier, it's just like taking tensor product in some way, but of a twisted sort. So here's the basic fact, but the harder fact, which I'm pretentiously calling the fundamental fact of arithmetic model, right? This is that if you start with a variety defined over Q instead of an arbitrary manifold, right? And then you take B and X to be rational points. Right? So yeah, sorry, here I see I've also again used a lot of notation inconsistently. These pi ones inside here, you can just take to be the topological pi one, or the complex points of the variety. But let me now finish what I was saying. If you take the unipotent completion and associated principal bundles like this, if the variety happens to be defined over F, over Q, and B and X are rational points, then in fact, these groups admit compatible actions of the Galois group of Q bar over Q. This is the key extra structure. So if I want to say this in a slightly mysterious form, I would say that these groups and principal bundles, therefore, if the axis, everything is defined over Q, have this kind of secret arithmetic symmetry, right, which gives it an extra structure. So, and these are what we're going to use. So this triple, the Galois group of Q, this unipotent completion of the fundamental group of the variety, and the unipotent completion of the torso of path. These are the concrete examples of the triples from the beginning when I was discussing arithmetic principal bundles. These are what we'll be using. So when you do this, you get a moduli space of principal bundles now, but because principal bundles in the sense, this non-abelian cohomology in the sense that I mentioned earlier. But now because this U is an algebraic group, these moduli spaces themselves become limits of algebraic varieties. Actually, the way I wrote it, you have to take a sort of double limit that I don't want to explain. So I'll cut it down in a minute and turn it into at least a single limit. But the basic idea is what I just said. Because U is an algebraic group, similar to what happens in geometry, moduli spaces of principal bundles tend to be algebraic varieties. Furthermore, you get a map from point to principal bundle, simply what I said. Start from a point and take the principal bundle of paths from your fixed base point to that point. That gives you a principal bundle, so you get a map from points to moduli spaces of principal bundles, and similarly locally and globally. Now the local versions turn out to be quite computable. A lot of the time, for example, the local versions will just have finite image. And when it doesn't have, so for example, so I said QP unipotent completion. So if you take V to be a prime different from P, it has a finite image. So that's quite, that can be described. And when V equals P, it becomes more complicated. That involves the computation of this moduli space as well as this map involves what's called p-adic Hodge theory. But when the theory dust settles around the theory that you use, you end up with a very concrete description of something called p-adic iterated integrals. The integrals similar to the Hodge theoretic integrals that describe maps from the points of a curve to its Jacobian, that describe this map very precisely and algorithmically when V equals P. So that's the general picture surrounding the local versions, so that you end up with a diagram like this. So this is a concrete version of the diagram I had earlier. Right? So you have these local moduli spaces, global moduli spaces, and maps from points that fit into this square. And so to complement now what I said a moment ago, this localization map is actually a map of algebraic varieties, and this is really the key point. Why? Inclusion of global points on inside product of local points. This seems to be a completely chaotic inclusion. But the lower horizontal map is simply a map of algebraic variety, or limits of algebraic variety, but it's an algebraic map. So in principle, the image is computable. So the idea is now with this geometric algebraic moduli space, you compute the image, find defining equations for the global moduli space inside the local moduli space, pull it back to the local points of the curve, and get defining equations for the points of the global points of the curve inside the product of local points. This is the idea. That's the general idea. Now it's quite hard to make this computable in practice, but the idea I think is very simple, and you end up with this process, which is in some sense, it seems unimaginable that you can somehow define global points inside local points using equations. So maybe it's a bit hard to get into that right now, but one should think about this process as really, so there are many different perspectives on this. As I said, it extends the picture for elliptic curves. That's a very important part of this story. But another part of this story, which I quite like, and which one can make precise, is that this should be really thought of, the equations you get here really should be thought of as being like an extension of Artin's reciprocity law. And you can make that precise. Why? What does Artin's reciprocity? There are many ways of viewing it, but reciprocity law says that if you take the variety GM, then you can describe to some extent the global points of GM inside the product of local points. It's the kernel of the reciprocity law, reciprocity map. Well, it's contained inside the kernel of the reciprocity map, and then you have to do more to say exactly what it is. But anyway, the idea is that the reciprocity map itself is a defining equation for the global points. And the equations you get in this case. No?
Can I just ask briefly? So, in the case of an elliptic curve, we should think that this pro-unipotent completion is something like ZP squared or something?
That's right. Yeah, QP squared. That's right. Yeah, it's just QP squared.
And so then, before you just had a torsion, like you had like Z mod PZ squared or something, but we should think that it's kind of analogous to QP squared or.
So what this thing, yeah. So I should have said maybe something more about like this. So if you take this group and you abelianize it, it just becomes QP to the 2G. And then there's an extension of that by something like the exterior product of QP to the QG. That's the first non-abelian level, and then it keeps going up. So for the elliptic curves, if you did this for elliptic curves, of course, it's just abelian, so QP to the 2G is all you get. But for higher genus curve, it's actually an infinite dimensional extension of something like that. So that's the idea. Okay. Right. Anyways, so you get these, what I think are actually very interesting equations defining global points inside local points, which in a sense, in a rather precise sense, generalize Artin's reciprocity law to other coefficient varieties. So from this point of view, the usual reciprocity law is just taking GM coefficients. That's why here I'm allowing other coefficients. So this kind of approach is also a non-abelian class field theory, in a sense different from the way people usually think about the Langlands program and so on. That's a point that I try to advertise somewhat more these days. Yeah, so anyways, this is just setting out is an inclusion what I just said in words. And I said this already in words as well, but I guess I forgot that I made a slide. If you just look at the p-adic component of this inclusion, right? If you project this down to QP, okay, maybe I didn't say it. I can now formulate a non-abelian effective modal conjecture. Well, I'll refine this in a second, but I'll give you the first version, which is, now, as I said, you take the equations defining this global moduli space inside the product of local moduli space, pull it back to the local points of the curve, But this is a product over infinitely many v, so this seems very hard to deal with, right? So even with the usual Hassa principle, remember, the Hassa principle says that there's a rational point if and only if there's a point at all v, you can never say anything about all v, right? So you have to do something to cut out the number of v's you have to check. So here what we do is you take this inverse image of the global moduli space inside the product of local points, and now let's project it just to the p-adic components, where p is the same as the qp coefficients that we're completing the fundamental group at. That turns out to be much more informative than all the other components. And so here's a kind of non-abelian effective Modal conjecture, which is a little bit vague the way I stated it just now, but I'll make it more precise in a second. So one statement is that you get exactly the rational points inside the p-adic points if you project the defining equations for the global moduli space pulled back to the product of local points. So that's part one of the conjecture. The part two is, of course, that this set is effectively computable. So in other words, this set here should be effectively computable, and that should give you exactly the full set of rational points. So this is the non-Archimedean approach that I referred to at the beginning for computing the set of points, not in terms of a priori bounds, but just sort of via a method of keeping on searching for more and more equations defining this and hoping that it terminates according to this conjecture as you search for more points as well. Now, let me refine that just slightly. Right? So, okay, so this is just telling the pictures, a story I already told, so maybe I'll skip this slide. Yeah. Oh, sorry, somehow I forgot. Yeah, sorry about that. Sorry, I was reorganizing slides from a number of different talks, and I think I pasted the wrong slide. Sorry, let me say this up. Let me say in words what I wanted to say here. The way you refine this conjecture is like this. This unipotent completion actually has a lower central series, and if you look at quotient modulo the lower central series, you get finite dimensional QP algebraic groups. And with the appropriate local conditions, this H1s also can become finite dimensional algebraic varieties over QP, which make everything more computable. So what you do is you find equations for defining the global moduli space as you go up the levels of the lower central series. Quotient, you get the abelian level, quotient modulo, the second level of the lower central series, third level, fourth level of modulo, all these quotients. And for at each level, you get more and more equations defining the global moduli space inside the local moduli space. Each of them, when you pull back to the local points, give you more equations defining the rational point. And the more precise version of the conjecture is that this story terminates in a way similar to the descent story, analogous to the descent story I told you for elliptic curve. Right. Sorry, I should have prepared some slides to say that more precisely, but sorry, I somewhat failed to do that. I apologize. But maybe what I'll do anyways is show you some of the equations you get. So the oldest version of this is when you look at this very simple variety of P1 minus 3 points. It's still a source of quite a bit of rich mathematics, P1 minus 3 points. Studying rational points or integral points on a curve like this, what it amounts to is the following equation. It's called the unit equation. You're looking for A and B such that A plus B is 1, but where A and B should be both invertible elements. So if you look at if you're looking for solutions inside points of this curve inside the ring like Z1 over N, where you just allow denominators that occur, the prime powers that occur in N, then the Z1 over N points of X just corresponds to solutions to these equations, where A and B are both invert units inside this ring. So that's kind of a very classical problem. But notice that the set of solutions has an S1 action simply tending Z generated by Z21 over Z and Z21 minus Z. So that's the general setup of studying these equations. Now, so for example, if you just looked at two integral solutions, inside this ring, then the only solutions are the obvious ones. You can easily write down some obvious solutions to an equation, 2 minus 1, 1/2. You can view this also as the S3 orbit of -1 if you want. And what the theory gives you is that it lies inside the zero set of two functions. These are the functions that you pull back from the global moduli spaces that I described schematically earlier. So, but the functions look a little bit complicated, but they're quite interesting when you look at it. They're combinations of logs and polylogs. So D2 here is a dilog plus a product of logs. What is the dilog? The K logarithm is defined by a power series like this. And then you have to analytically continue it where it doesn't converge. So you can do that using iterated integrals. And this, where does this equation occur? It occurs inside the p-adic numbers. Remember, I ground these equations and projected it down to QP, right? So when all that dust settles, what you end up with is equations that define the integral solutions, the solutions to the unit equation as lying inside the zero set of these equations, or these zero sets of these p-adic analytic functions. So this all occurs inside ZP. Right? Where you've chosen a P different from 2, by the way. So this gives you a flavor of the kind of equations that you end up with, I hope. The coefficients here are all p-adic zeta values or p-adic special values of these polylogs, as you see. So I should point out that you can check whether this inclusion is an equality. And so these guys, then Ishai Denko and Stefan Bevers, they did a computational check of this for, unfortunately, for not very large primes, for primes up to 10,000, less than or equal to 10,000 or so. Apparently, I don't know much about actual computations, but it apparently gets very expensive as P gets large. But for all the primes they've checked so far, then some other people check some other range of primes and so on. But for all the checks that have been set, the primes that have been checked so far, you get an equality here. So these are kind of computational confirmation of the conjectures. It's hard to theoretically prove that this is an equality because these functions are still a bit hard to understand. But everything that's been checked numerically so far, it confirms the conjecture and proves an equality here. Maybe I won't describe this work too much. This is written work that arose out of the Arizona Winter School that continues this work in some ways with something called the refined Selmer schemes, but I didn't. Oh, by the way, these moduli spaces are called Selmer schemes. That's what I called them at some point. We've been using that terminology. So you can continue that in some way and say more things. But maybe what I'll tell you is about a rather very nice application. Well, there are some also qualitative results and so on. But maybe I'll tell you about a very recent result of these 5 authors, Jennifer Balakrishnan, Nathan Dogra, Stephen Mueller, Jan Teichmann, and Jan Wong. So what they did is they studied a specific modular curve that's been quite intractable for many years. So this is called the so-called split Carton modular curve. What you start out with is the full compactification of the modular space of elliptic curves with full level and structure. So this is the standard modular curve. Then you mod it out by the normalizer of a split Carton subgroup inside GL2 of Z model. But when you do that, you end up with a curve defined over Q. So when you take n to be a prime, so this is a split Carton modular curve of prime level, Yuri Bilou, Pierre Parang, and I forgot the first name, Rebolledo, had shown that the rational points on this curve consist entirely of cusps and CM points for all primes larger than 7, as long as P is not equal to 17. So they posed this problem. So this goes back to a question of Serre, which I'm also not describing today, but P equals 13 was quite intractable, so they called this the cursed level because nothing seemed to work in that case. So in other words, this is exactly a situation where you had a certain collection of rational points, the cusps and the CM point, and you could have just, it was very hard to figure out that these were all of the rational points. So these 5 authors recently checked this, right? So I'll skip this discussion of Serre's conjecture. And so this is the equation. I'll just show you this equation. This is the equation of the curve, which was found by Boursu-Baran. And this is some picture. I don't know how it was generated, but Jennifer Bauer-Cushman sent me this picture upon request. It's some schematic representation of the curve. And these are the 7 points on the curve. So as I said, the hard part was checking that there are no more. So what they did is, so in this case, you come up with a bunch of equations similar to what I showed for P1 minus 3 points. And you show that there are enough to check precisely that there are no more than this. You have to, of course, prove some things about the bounds of the computations that you do with p-adic analytic functions to prove this on the nose. But that's what they succeeded in doing. This was quite a nice recent result. So instead of discussing more examples, maybe I'll close today with some crazy speculation. As I said, since this completely stupid idea yields some result, I'm tempted to throw around more stupid ideas. So that's what I'll do at the end of the lecture. So this is speculation on rational points and critical points. So what do I mean by that? Well, you see, this inclusion of or map from the global moduli space to the product of local moduli space, as I said, these spaces are really very much similar. These are non-Kimmian versions of the kind of moduli spaces used in counter-engaged theory. They're a bit different in the sense that usually in gauge theory, people study semi-simple groups or reductive groups, and most here you have a unipotent group, so the flavor is somewhat different. But in any case, the fact that there are these global bundles sitting inside collections of local bundles is very similar to how, say, solutions to Euler-Lagrange equations in gauge theory, lines are the arbitrary connections, including, say, distributional. And so that's an analogy I've had somewhere in the back of my mind for a long time. But I didn't really think about a way to make this precise other than just at a philosophical level. But you see, what happens is that, so in other words, it's tempting to think about the equations defining the image of the global moduli space, which, as I pointed out, these are very important for computing rational points on the curve. I'd like to think of them as being like classical equations of motions for gauge fields. Well, but the point is that when X is a smooth and projective curve, which is the case most of interest, the rational points are the same as the integral points. Then it turns out that the moduli spaces we're actually interested in, well, it's not just the image of the global moduli space. There are additional constraints coming from this integrality, and I'm not going to describe exactly what they are. They are Hodge theoretic or integrality conditions. There's another subspace of product of local moduli spaces given by integrality or conditions and Hodge theoretic conditions. And we're actually interested in this intersection. So from the point of view of our sort of fashionable geometry of the last 10 or 15 years, we know that when we are interested in a set that's an intersection, we should somehow retain the information that it's an intersection. That's an extra structure that it's foolish to discard. Right? And so that's what I've been thinking about without too much success recently. But as I said, it's okay. I feel like I want to indulge crazy ideas. So how does one use this intersection structure? Well, to make it somewhat more similar to the techniques that people actually use in derived geometry, they want to make things a bit symplectic. And so one very stupid way of making things symplectic is to replace this unipotent group by a twisted cotangent bundle. So this twisting refers to twisting the Galois action just in the cotangent direction. You can make sense of this and get another cotangent bundle, which is also a group with a Galois action over Q. So you set up a moduli space for this guy, principal bundles for this thing. And when you do that, the local moduli spaces actually become symplectic varieties over QP. They're not just algebraic varieties, they're actually symplectic algebraic varieties over QP. And the key point is that the image of the localization map, as well as this product of local moduli spaces that satisfy integrality conditions, they become Lagrangian subvarieties. And some of you know probably what happens in this situation, that when you take the intersection that has a -1 shifted symplectic structure, so-called. And the implication is that you can Zariski locally look at this as the critical set of a function. So this is a theorem of many people, I think, but I've quoted 4 authors that I know about. I'm very bad about the background literatures. I hope you don't hold it against me. But anyways, this has a -1 shifted symplectic structure, and in particular, it is locally the critical set of a function. The way this construction works, it can be thought of as the critical set of a function defined on this moduli space, on this local moduli space. So then what's the implication? Well, here we're interested in the actual points of the curve that will map to the global moduli space. It will also map to the portion of the local moduli space that maps to that subspace satisfying critical condition, the integrality conditions. And we're interested in the intersection, so that will lie inside the classical scheme underlying the derived intersection. So in fact, the global points, the integral points of the curve, lie inside the inverse image of this moduli space. Well, so what does that mean? That means that there's actually a function whose critical set is this moduli space that pulls back. So that, in other words, it somewhat realizes this idea that this really is solutions to these, the image that we're interested in. The portion of the image that we're interested in should be a solutions to an Euler-Lagrange equation that then pulls back to equations defining global points on the inside the local points. So how to realize, so this picture itself is true, I'm not speculating here, but how to find these equations in some useful way, how to express that critical point equation as something useful. It's something I'm speculating about without too much success, but I'm mentioning it again today because the idea itself is so attractive. So I'll just finish with something of a joke, but which I take seriously. You can regard it as a joke. That's this picture, right? So Fermat was, in my view, one of the really great scientists of the 17th century. People, even mathematicians, don't often know this because they don't quite realize the full range of his activities. Of course, he was a very influential guy in the creation of modern number theory. At that time, so just to make a few historical remarks, he worked on a lot of Diophantine equations and some of the equations that have become famous, but it's according to historians, very few people were interested in it. He tried to interest his friends. He corresponded with so many great scientists around Europe, including Galileo and Hobbes and so on. But people were interested in sort of serious science and geometry, and number theory seems to many people to be kind of a trivial pursuit. So he seems to have been rather isolated and somewhat frustrated by other people's lack of interest in Diophantine equations, for example. But of course, he did lots of other important science, including, for example, the creation of modern probability theory with Pascal. He also created coordinate geometry independently of Descartes, and they really somewhat fought bitterly over this priority. But he also used the first least action principle, formulated the first least action principle to explain the refraction of light as it goes from one medium to another. So for me, it's quite interesting. So this least action principle, of course, it's what led to the Euler-Lagrange equation and all the action principles of modern physics, the gauge theoretic ones in particular. So it's somewhat interesting that in this diagram, it suggests the possibility of finding rational or integral points to equations using solutions to Euler-Lagrange equations. So just as a kind of fanciful completion of a historical study that started in the 17th century, it will be very nice to be able to do this in a useful way. Okay, thank you very much. I think that's all I had to say.
Thank you. Are there any questions?
Yeah, can I ask you, please? I think maybe Jordi also asked something similar. So your effective Mordell conjecture, so for genus, which is not interesting for you, genus
one?
yes, right? For genus 1, is it the same as Swinnerton-Dyer conjecture, or it's actually not interesting?
No, yeah, in essence, it's a bit of a limit of this. So I may be saying this slightly inaccurately, but in essence, it ends up being the same as this Tate-Shafarevich, finiteness of Tate-Shafarevich that I referred to earlier. It's essentially the same. Another question? No, Jody?
Kind of alternative point of view on the art and reciprocity law.
Right, right.
Could you explain what you were saying again? I just didn't.
Yeah, sorry. Yeah, sorry. Actually, I originally had another slide also, which I didn't think that I'd be able to use, so I just got rid of it. But okay. So maybe this slide is the best one among the ones I have available. So the idea, remember, is that you study this algebraic map, localization map that's an algebraic map, try to compute its image. In particular, find functions that annihilate the image of the global moduli space inside the product of local moduli spaces. And you pull that back to the local points of the curve, and then you get functions of a nature that's essentially p-adic analytic when you've taken QP coefficients here, that annihilate the global points inside the local points. So that's what you get. What I'm saying is that this is similar to the statement in art and reciprocity that says that the Q star is killed by the reciprocity map inside the idels. And one can make that analogy much more precise. So one doesn't view that as a Diophantine statement normally. I think it is a Diophantine statement that somehow the annihilation of global points from the reciprocity map is a way of a portion of identifying the global points inside the local points of GM. And this is a version of that. And in order to make this precise, so in a separate work, what I've done is I've used some kind of combination of the profinite and unipotent fundamental group to define a sequence of reciprocity law on this product of local points. There's a first reciprocity map, sorry, the sequence of reciprocity map, first reciprocity map, second reciprocity map, third reciprocity map, and so forth, that goes to a sequence of groups constructed out of cohomology like this, but it's graded pieces of cohomology like this. And the way they are defined is that the first reciprocity map has a kernel, simply as a pointed set. And on the kernel, the second reciprocity map is defined. And on the kernel of that, the third reciprocity map is defined, and so on. And you keep going. So you have an infinite kernel of these iterative reciprocity maps. And the generalization of Artin's reciprocity law is that the global points of the curve lie inside this infinite intersection. That one can formulate for any reasonable variety, actually, not just for curves. That actually you need some conditions about the Galois cohomology, some conditions on the torsion of Galois cohomology. But modulo that, you can for very general varieties, you can define these iterative reciprocity laws, whose infinite kernel contain the rational points. And that's somehow part of this picture. And so here I'm looking at a portion in order to make things very computable. But there's a way in which there's a non-abelian reciprocity law with general coefficients, not GM, that underlies this story. That's what I was trying to explain earlier. So, you know, there's not only one non-abelian reciprocity, I guess maybe that's what I was trying to say.
Mm-hmm.
On the other hand, this is again something I can't quite go into right now, but how does one actually produce this equation? It's very, very hard work to do this directly computationally, right? In production of these functions that annihilate the global image here, it works. It actually works in this way in some cases, but it's an idea that I haven't quite been able to realize. Production of these alphas should be very similar to technique of Euler systems that occur in many parts of the theory of Galois representations, and their connection with usual Langlands should come in as well in production of the equations.
Are there any other questions? All right, if not, let's thank Minhyong again.
Okay, well, thank you for your patience and staying up till late at night and listening to this.
Oh, thank you.
Yeah. Okay, well, I'll sign off, but then I hope I can visit Sydney in person one of these days, but in a better world.